Good morning everyone. In this lecture, we will discuss about the Bode phase plot. So Bode phase plot is nothing but kind of XY plot, and for defined frequencies, we have to just get the value on the transfer functions on the calculator and put the values to get the Bode phase plot. That is very simple. How we will solve by taking two examples. One is this: any transfer function is given to you, and from the transfer functions, I have just written the transfer function in time constant form first of all. So next step is that in order to get the phase, what we have to do, we have to g omega, that is 100 into 1 plus, just put j omega instead of s, 1 plus this is j omega by 2, 1 plus this is j omega by 5, right? So you know the basic concept of phase, that means angle. What is this? Basically that is the phase is nothing but the angle, and that is denoted by angle of j omega. So how the angle is calculated, that you know, because this is very simple and very easier procedure to find out the phase from any given that means complex quantity. And this is a complex quantity having several terms here. So how to find out the phase? See, we will have to find out the phase. Like the procedure I see, this is 100. What I follow is that just make it real plus imaginary. Every term given to you, either it is real only, either it is imaginary only, any form given to you, you have to just this expressed as real plus imaginary. So 100 means we will write at 100 plus j0, nothing else, right? So once this is 100 plus j0, this is remain same by 10 by this is 1 plus j by 2, 1 plus j omega by 5. Now what I have to do, we have to get the angle of this, and you know the concept of angle is like tan inverse of this. That means, say for example, any complex quantity a plus jb is given to you. Now angle of a plus jb equal to tan inverse of imaginary by real, as simple as that. So each of the factor will have to find out the angle. So just step by step I will describe it, such that you can do any kind of problem and solve the phase, or to get the phase of the system, right? So first of all, we will consider 100 plus j0 in the numerator part. So you can say this is 100 factor is 100 plus j0. This is in the numerator. What is the phase corresponding to this? This is tan inverse 0 by 100. That is tan inverse 0 means 0 degree, right? There is no confusion in it. So this is the phase corresponding to this. Now the phase corresponding to I will write in a phrase part. So phase corresponding to this term of 1 plus j omega by 10. So that is tan inverse omega by 10. This is your imaginary by real. So tan inverse omega by 10. So this is the factor, that is phase corresponding to this part. Now coming to the denominator part. So the factor is 1 plus j omega by 2. What is the factor? That factor is tan inverse omega by 2. You see. Similar, 1 plus j omega by 5. What is the phase? That is tan inverse omega by 5. Now you get the total 4 phases corresponding to 4 factors, right? So what are the total angle corresponding to the numerator part? So total angle corresponding to the numerator part means phase are normal additive in nature. So the phase contribution due to this plus phase contribution due to this. So the phase for numerator, I will write tell it as numerator. So this is the phase due to this is 0 degree plus of phase due to this is tan inverse of omega by 10, right? So this is the phase for the numerator part. And what is the phase for the denominator part? Phase for the denominator part, I write for denominator part is equal to this part, this plus this, because these are the two factors in the denominator. So this is tan inverse omega by 2 plus tan inverse omega by 5. Okay, now phase of g omega. So g omega having phase in the numerator, phase in the denominator. So phase in numerator minus phase in denominator. That is the total phase. As simple as that. For any factor, first of all, you have to convert it into the sinusoidal transfer functions. Then take the phase of each of the factor given to you, and if these factors are in the numerator, just numerator total phase will be the addition of all these phases. So this is phase in numerator, means this plus this, and the total phases in the denominator will be equal to the phase contribution due to each of the factors which are residing in the denominator, right? So this is the phase in the numerator. So ultimately tan inverse omega by 10 minus of tan inverse omega by 2 minus tan inverse omega by 5, right? So this is the expression for phase. We can write it 5. Now what then we have to draw? We have to draw the phase angles. That means we have to find out the phase angles corresponding to different frequencies. And I have already said that the phase plot drawing is very much simple. What you have to do, we have to just make a table like XY graph plotting, right? So for that, one basic thing is that you have to rewrite this what you call it, the transfer functions, right? So transfer functions, this is the expression for the phase, and I will write the transfer function again. Here we have written the transfer functions in the time constant form. And what are the different corner frequencies we get from this factor? What is the corner frequency? You can tell it corner frequency is 10. What is the corner frequency for this? This is 5. And what is the corner frequency corresponding to this? 2. So the 3 corner frequencies we get, right? Why these corner frequencies are required? Because when you make the table like we get the table like this here, we will have to make the table. And what is the procedure? This is your omega and this is 5, right? So what are the different values of omega we have to take to get the curve? Like see in your Bode plot, this is your semilog graph paper, and you see this is your 0.01 to this is your omega 1000, right? This is your omega is equal to 0.01 to omega 1000, and in between there are 5 divisions, right? And here in the second, this is the bottom side of this graph we will use for 5. So that means the frequencies again have to vary from initial value to infinity. So we need to consider the initial value of this frequency for calculating this that is completing this table, that is equal to 0.01. So this is 0.01 is your, this should be your at least one value we have to take. And how to find out the Bode phase plot? To make this phase plot, we have to get the value of 5 corresponding to each of the frequency we will get here. So what are the different frequencies I will take? I will take, say, all the values which are nothing but the corner frequencies. So we will have to consider some values of corner frequency. That is the procedure, standard procedure I follow, and by this procedure you can solve this any kind of problem. So this is your 0.01, that is initial frequency. Next we will consider the corner frequencies. So what is the minimum of this corner frequency? 2. We just make a space between this and 2. Next corner frequency is 5. These are the standard values. Next corner frequency is 10, right? So how much value we have to take? That is very important. How much frequency you have to take? We have considered here in this case, depending upon the corner frequencies. First of all, you have to consider the frequency omega is equal to 0.01. Next, what you have to consider? We have to consider all these corner frequencies 2, 5, 10, and if there are more corner frequencies, all these corner frequencies you have to incorporate, no problem. Next, in between these two values, say 0.01 and 2, you can have any value, right, to get the just a smoother graph. What is this? I can take it 1, you can take it 1.1, you can take it 1.5, whatever you feel. And between 2 to 5 there are so many, several numbers you can take. So better you take nearly 3, such that it lies between these two. that's just halfway around this. To 5 to 10 we can take it 8, we can take it 7, you can take it 6, whatever you feel. And one more thing is that we have to consider one last value at the end, that is here, which is just 50 times multiplications of this last corner frequency of the resultant value. Okay, so what I call it, that value is just 50 times of this value. That means this is 500. Okay, what I call it, I have just considered a point of omega which is 50 times the last value. I may call it like you see that value, last value of omega, that last value omega we have to consider, that is a convention. So last value of omega is equal to 50 times the maximum corner frequency, right? So last value of the omega in this table, the first value, initial value omega is equal to 0.1. all these corner frequencies we have incorporated here, and in between any value you can make, and the last value of this table will be the 50 times. Here the maximum value of the corner frequency is 10, so the thumb rule is that you have to take the last value 50 times. So 50 times means 50 into 10, that means that is your 500, right? So omega is equal to 500 I have taken here, and in between you can take any value 100, because 10 and 50 within this you have to take another value. So that is the procedure to find out the frequency. Once the frequencies you have just obtained in this table, where you have to do, you have to just get the calculator and calculate this value of phi. Omega is equal to 0.01, put this and get the phi. So this is your phi 1, this is your phi 2, this is your phi 3, and all this value. Just okay, you just get phi versus omega and all this value you have considered. Then what you have to do, once you get these values completed, then only you have to just scale the semilog graph paper in the lower, that is the bottom part of this graph, and where I have already shown you that the angles, that is the phases, are normally starts from 0 degree toward downward. So 0 degree, minus 90 degree, minus 180 degree, and so on. I'll just make a scale update, and I am just taking some arbitrary values, because for this particular actually your GS, that is transfer functions, I have not calculated it. Say for example this is minus 70 degree, say maybe minus 80 degree, minus 90 degree, minus 95 degree. All these values are arbitrary value. Say minus 170 degree, minus 185 degree, minus 200 degree, right? Anyway, these may be positive, these may be negative, these may reach, see here the range. Just concentrate on the range. What are the ranges? Arbitrarily I have written minus 170 degree, minus 185 degree, minus 200 degree. The thing is that you may get these values, like say for example you may get the values minus 179.1, minus 179.2, minus 179.3. But I have written the values like minus 179.1, minus 179.2 like this, because our aim is to get whether this graph actually, whether there is any frequency where the phase is crossing minus 180 degree line. So crossing of minus 180 degree line is very important. Whether any omega is possible for which the phi is equal to minus 80 degree. So that is the very important issue. So that is why there may be some problems where you can find this you are just increasing the value of omega is equal to 0.01 to 500, 5000 also. You may take any value, any larger value, but there will be no chance to get phi is equal to minus 180 degree. Maybe the last value is minus 179.8 degree. That means that graph is not actually touching the minus 180 degree line. So minus 180 degree line in the phase graph is very much important. So that is why how you have to be very careful whether wrongly, mistakenly you are calculating the value is either minus 180 degree and above. Maybe you feel that the value is minus 179.8 degree at omega is equal to 100. So maybe when you put omega is equal to 1000, this may be minus 180 degree plus. No. So there may not be any chance of that, because the system is so designed and Bode plot is so fantastic in this case. You can see the beauty of it is that you go on increasing the frequency up to infinity, but it will never touch the minus 180 degree line. So that is very first, you know, that is the so much nice thing. Okay, so that is the way by using this table you can have to plot this graph. So I will try to just draw a graph. See, here I have just drawn one 5 versus omega table. I have calculated one table, right? So based on that table, you just put omega is equal to 0.01. So angle maybe minus, say, minus 75 degree, and omega is equal to all other values. You can have the values like this. And finally, all these values freehand you have to just draw. Just you have to draw the line like this. So this is your phase plot, as simple as that, nothing else. And the thing is that here you see there is a point when omega is equal to 500, the value is minus 200 degree. So that minus 200 degree means this graph is touching this minus 1 degree line. So that line is very much important. Again, I will tell you that this line is very much important. Maybe there are certain graphs where you will find this graph will just go like this. That means there is no chance of touching this minus 180 degree line. So that is the procedure how you can get the phase of any system. So the zeros along with the first order factors I have discussed. Now I will consider a type 1 system with the second order factor, and we will try to find out the phase corresponding to it and how to get the phase. And similarly, this procedure will remain same. That means in this semilog graph paper, this is your omega axis, frequency axis, and above of this phase line there is definitely, you see, there will be the your gain, that is dV, that is your magnitude. So this is your gain curve. So gain curve is here, and you will find out the phase curve here by adding this frequency omega is equal to 0.01 to infinity, right? So this is your phase curve, and above of this, corresponding to this, you can draw the magnitude curve. So that will in total gives you the Bode plot, right? So I will concentrate here is second part, that is a type 1 system with second order factor. We will find out the how to get the phase. So that is all about the that will be the completion of this phase characteristics for the Bode plot.